So thanks everybody for coming here. We're the Solar Panthers from Hanover College, small liberal arts engineering school in Indiana. So we're going to start off talking about team structure, kind of how we approach a problem. So for system design, Taylor's going to be joining us here when he can. He did a lot of the modeling and actually drawing up the designs. Ty Allen should be trying to join here. He did system distribution, did a lot of that analysis. And then Jordan and I, we did the financial analysis, getting the PPA and all that set up to make sure it's actually feasible. So before we get started, these are some common acronyms you'll see. I'm sure most everybody here is used to them. Okay, so go ahead and take this. Our approach to the system design, our first step, our design was to try to understand really what the problem was and really get a clear, concise problem statement to work off of. And of course, the most important part of the problem we saw was that this needs to be, paid off 20 years and meet the minimum load. So we really just kind of focused our design around the PPA over that 20-year period. And then once we completed that, we compared the on-roof design to an off-site design, and we kind of decided which one would yield, the biggest energy production and savings to get the best possible design. And then, of course, we use the Aurora Solar software program to draw this all up.
Yeah, so here's just a summary of our approach to how we expected our system to operate. Obviously, we chose our panels to be mounted on the roof with a fixed tilt. And then also we use our panels to be connected to one microinverter per 4 panels because we created our own custom microinverter. And then obviously our batteries we used in accordance with the REL software analysis to optimize our system performance. So here's just a kind of summary of what our system design was. Obviously not going into too much detail here, but we ran a Irradiance profile, got 80% solar access, which is a little lower than what our initial design was. But that's what we decided to go with, which we'll explain later. Use a 13-degree tilt, and then a 1/2-inch panel spacing with 18-inch row spacing. Then we determined which microinverter and which panel combination would be best to use. Obviously, as I mentioned earlier, our microinverter wasn't already in Aurora Solar, so we had to use our own custom one. And then obviously, we also deleted panels for HVAC units and added in a 3-foot exclusion zone around the edge of each building in accordance with fire codes and for safety reasons. For our offsite design, we chose a location in Gotham Run, Virginia, which is just a big open field. About that far away from Crystal Parks.
Sorry about that. I'm having a little trouble controlling the screen. There we go.
Okay. For our offsite design, we used 100%. Obviously, we had to meet the 100% solar access, and we used the SunPower X21 470 panel. We used 15-degree tilt, and we just decided to use the sample string inverter. We met the 100% offset requirement, and we just chose this location because it really didn't look like it offset too many people or too many objects, and it was kind of in a remote area, but not too far away. Yeah, so here's just a rundown of what our panels were and the specs that we had. So it's an LG panel, 60 cells and 17.5% efficiency, 300 watts. It's a little lower on the watts and efficiency side, but definitely saved us a lot of money. And then here is our microinverter, which we researched and had to input in Aurora because it was custom. So here's just the specs that we got from Amazon. So it's 1200 watts. 95% efficiency. It's a single phase. And then our total project sizes, which we pulled from Aurora. So our total rooftop design, the DC size was just over 1,800 kilowatt hours. And then our offsite design was 12.2 megawatts. It's too big to run the simulation, at least on my laptop, to get DC size. But that was the total megawatt size that we had. And then for our rooftop design, it was 1.4 megawatts with the annual production of almost 1,600 kilowatt hours. And then for the battery, we use the Reop Life software to determine the ideal battery size, and then we calculated that over a 20-year evaluation period. So it suggested that we use a battery size or capacity and power of 177 kilowatts and 360 kilowatt hours, and then it calculated that our projected savings over those 20 years using that battery size in our rooftop design would be over $125,000.
And these are the on-site plans these are the buildings for the Crystal Park division. Each building would have all of the panels as you see on the top of the buildings. This is our off-site plan. The off-site plan, this is something like 70,000 panels, something ridiculous. But yeah, that is the off-site plan, essentially just out in the big field. Continued. Each building, as you're going to see scrolling across, has its 3-foot exclusion zones all the way around. The HVAC areas have been completely cleared from solar panels, as well as the 15-inch row spacing for the spacing, as well as maintenance crews to go in and out to fix the panels as necessary.
And here's just a rundown of our shading report that we pulled just directly from Aurora itself. So you see there's, it gives you radiance data, it gives you, how many panels are in each building, the access that's going to have, production, pitch, stuff like that. So, and again, another rundown of this is just showing annual production. So to calculate all this and what we did, basically we put in, our inputs are put into the allergy generation profile, which we had to create a macro and do some stuff in Excel to get that to run. Once we had that for all of 5 buildings and we had it in that compatible CSV format, then we uploaded that into Aurora. And then we needed that file to do our simulations and get an accurate estimate of what our system design performance is going to be. And here's just a source of our Irradiance model.
So I think Ty was able to make it, but I can go over this real quick. So he did the distribution analysis. So he took what Taylor had created over in the Aurora software and put it in the OpenDSS. Basically, he just simulated the energy output over 1 year, and we were able to expand that over a 20-year period. And he just basically was making sure that we met the minimum voltage output, and we were within a target tolerance because of the size of the project. We were able to come up with a tolerance that said, if we were doing this in real world application, we would have losses such and such that it would be acceptable. And then here's a quick overview of our financial modeling that Jordan and I did. We did a financial model for all the designs, and then we decided, with PPA and then, the production we're getting from the roof design to go ahead and stick with that. So we got 2.15 cents per kilowatt hour as PPA over the 20-year period. And we were fairly happy with that because if you compare it to prices in the region, this is in dollars per megawatt hour. So if you divide these numbers by 10, you'll get cents per kilowatt hour. As you can see down towards 2018-19, we're getting around that 2 cents. So we were very happy that we were able to stay within average prices in the region.
Okay, so for the process of optimization, we really just wanted to examine basically everything in our system. We wanted to look at, what panels we were using, how they're oriented, tilt, spacing, inverter selection. We wanted to, look at just our whole system and evaluate it and think about what we could do better. So just for like a little summary of, what innovation that we had, most of our stuff was pulled just from online research. I mean, we weren't trying to reinvent the wheel or anything. But one innovation that we had, obviously, as I've mentioned, multiple times before, was the fixed solar microinverters that we use. It was a little bit of, it wasn't a standard method using that microinverter, which took the input of 4 panels as opposed to the standard 1 inverter per 1 panel method that's common. But use of this microinverter saved us a lot of money and didn't sacrifice much system performance at all. The last point that it was on that slide was additionally, if we used a lower solar access minimum because of our panels. So we went for more number of panels than, 95% solar access because of the price point of our panels. They were a lot cheaper than like smart modules. And then system operation. As I mentioned before, we use fixed pill panels as opposed to ground mount trackers and smart modules. This kept our system costs down, specifically our equipment costs. And then we also chose to use microinverters instead of string inverters because of the size of our system. I think we had over 4,000 panels in total. So, if a couple of panels go down, it's better to use microinverters because, the entire system performance isn't affected when you have panel failures as it would be in string inverters. And then for our optimization, we first started looking at the angle of our panels, and we found that between 10 and 15 degrees, we did a little bit of trial and error as well, but about 10 to 15 degrees would be ideal for us. Obviously, with 10 degrees being for hotter climates and 15 being for lower. So being in Virginia, we chose 13 degrees. And then after doing simulation, we saw our system production jump in our initial design to 9% each. So it jumped from 6% to 9% as when compared to our progress design. Then we adjusted our orientation of the panels to point them true south. We actually, when I was, me and Cornell, I don't know if Cornell is here or not, but when me and Cornell were doing the system design, we actually found out that all our panels were facing away from the sun. So they're facing true north. And then, so once we did that and accounted for our magnetic declination, which we calculated online, found 10 degrees west. So we just moved those negative 10 degrees on Aurora. And then, as we mentioned before, we also added in that exclusion zone. Then we looked at our equipment selection, and we found our microinverter and panel were far too expensive. We were using a smart module from SunPower, and I think we were using an N-phase inverter. The N-phase inverter was like one of the best on the market, but they were like $175 each. When you have 4,000 of them, that adds up. So our system was it was over 1.5 megawatts at the time, and our equipment cost alone was like over $5 million. So we said that's not going to be a cost-effective design. So
Taylor,
we scrapped it.
I apologize for interrupting you, but we are at time, and so to preserve the order of things, we're gonna shuffle along here to the Q&A.